Okay, all right, thank you. So today I'm talking about a project that I'm working on to optimize ventilation and filtration systems in specifically classroom environments. And so the overview is that existing mechanical ventilation systems don't do a very good job of managing indoor air quality in buildings, and then they also often consume excess energy. And the main, mouse show up here. That would be, oh, there's a pointer. Look at that. My main interest here is, so here's an example HVAC system, and the air returns from the room and it mixes with some outdoor air and is supplied to the room, and then the building leaks the air out as well. And so my main interest is in controlling these outdoor air dampers, which change the fraction of the return air versus the outdoor air. And we might want to make a different decision on that based on what's happening indoors and outdoors. And so my goal is to test what I'm calling the IAQ energy controller that will retrofit controls for this damper system. Essentially will change what those dampers are doing. And the goal is to minimize, so increase outdoor air to minimize infectious disease transmission, to reduce exposure to pollutants outdoors, and to minimize HVAC energy consumption. And so then what I am trying to characterize is the potential of this control for impacting these metrics as depending on where it's installed around the country. So the challenge is that ventilation has benefits and drawbacks, and that changes depending on what's happening. So as we increase ventilation, we bring in more outside air, we reduce the indoor concentration of respiratory aerosols that we're breathing all the time. We reduce the concentration of chemicals, volatile organic compounds, and off gas from furniture. We reduce energy use when the outside air is at a nice temperature, essentially. And increased ventilation is associated with reduced absence rates in schools. The drawbacks are that if our outside air has particulate matter in it, we're now increasing exposure to that inside the classroom. Often outside air has elevated ozone, we're bringing more ozone into the classroom. And then if the air is too hot or too cold, we have to condition it. And finally, as we bring in more outside air, we have more outside particulate matter we're filtering, and then we have to increase filter maintenance. So, and then on the filtration side, filtration has a lot of benefits. We can, when you move air across a filter, you remove respiratory aerosols, and you also remove particulate matter. But the drawback is there's a little bit of energy use with increased filtration and also increased filter maintenance. We can also run portable air cleaners. And those are pretty energy efficient. The main drawback from those can be noise. So just to talk briefly about what the state of the art is, essentially what is done currently. And most classrooms just have fixed rate ventilation, meaning when the students are in the classroom, the fan for the HVAC system turns on and it provides one ventilation rate the whole time, and then it turns off. The next best thing that can happen is you have an economizer. And what that means is when the outside air temperature is below a specified limit and the classroom needs cooling, it's going to bring in outside air for cooling. And so classrooms have are very densely occupied. And so they have large cooling loads. And so we could need cooling. It might be, 10 degrees Celsius outside, and we still need cooling because we essentially have a room full of little heaters, right? And so that's what an economizer does. Then there's demand control ventilation, where basically we say, okay, we're all breathing and exhaling CO2, and we're just going to bring in the amount of outside air we need to keep that CO2 below a set point. And then the best state of the art currently is where you combine an economizer with DCV. So you run a fixed CO2 set point, and then if you need extra outside air for cooling, you go to a max outdoor air. So my approach is I'm essentially adding additional logic to an economizer plus DCV approach. So if the outside air PM 2.5 is low, and we can debate what low means, that's part of the objective here, and the outside temperatures are within a nice range, right? So that, and again, what does nice mean? But basically, these are temperatures at which you would say like, hey, let's open the windows, right? Like why, like let's bring in as much outside air as we can. And then conversely, if outdoor PM 2.5 is high, then don't economize, right? Because one of the biggest problems with economizers currently is that it's a November morning, school is open, there's a wildfire in the area, the students come in the classroom, all of a sudden the unit goes, we need to cool, opens the outside air damper all the way, dumps in all this smoke, right? Then the facility managers go around disabling all those economizers. And then the question is, do they ever get put back, right? And so this essentially automates that. It says, okay, if PM 2.5 is above some high limit, we're not gonna use economizers right now. And then also, essentially if the situation is bad, we could also raise our CO2 set point to limit ventilation. And we could have a portable air cleaner in the classroom and we could run it at a high speed to reduce exposure to, we've now raised the CO2 limit, so we're breathing more of each other's air, right? So we could run a portable air cleaner to clean that air, both of smoke and respiratory aerosols. I put this slide in here just so if people want to look at it, essentially look at it later. This is the detailed control logic that accomplishes what I just described. At the end of the day, what I'm trying to do is achieve indoor air change equivalent for respiratory aerosols, meaning that there's a new ASHRAE standard for reduced infectious disease transmission. And essentially the goal is to figure out, we're all exhaling these respiratory aerosols, let's get them out one way or another. We use outside air or filtration or a portable air cleaner, and essentially those things working combined. I'm trying to achieve an air changes per hour of like 8 to 9 air changes per hour in the classroom, regardless of what mode we're in and what's going on. So I built a model using Energy Plus. Is an building energy modeling program. And basically what that does is now I'm building a energy model, but also a simulation of particulate matter exposure. And so I wrote my own program to calculate particulate matter, and I wrote I'm using Energy Plus to calculate the energy impacts, and essentially what the Energy Plus model feeds into my particulate matter model. But the point is, in order to run an energy simulation, you have to know something about the weather. You have to know you have to have a weather year file that you're simulating your building in, right? The building has to be somewhere, it has to have a weather file. What's really tricky is to simulate the particulate matter, you have to have a particulate matter file. Well, people have spent decades building typical weather years, but there's no typical particulate matter data anywhere. So we spent a lot of time, we took, and Christy helped with this a lot. We took 5 years of real world weather that was compiled by white box technology. And then we essentially built PM 2.5 particulate matter files from EPA data that is coincident with that location at those times. So now we have a simulation, we can run weather and we can run PM 2.5. The trick is that there's a lot of monitoring stations all over the country, but they go down for small periods of time. So you have to like strategize as to like pull data from the next station, or what are you going to do? So we now have all those, all that data, and I think Chrissy's going to put it up on GitHub. Anyway, and then I run the 3 different types of,
Here's a question. So for how many sites?
14 cities across the US.
14 different cities across the US.
Yeah.
And are these kind of urban locations?
You'll see them shortly here.
Whitebox lets you put those on GitHub.
We're putting the PM 2.5 files on GitHub. We're putting code on GitHub where you can basically specify a location and it'll build you a PM 2.5 file for that location for whatever period of time you want. So
Got it.
yeah. So we run I run a fixed ventilation controller, a state-of-the-art economizer plus DCV, and then this IAQ energy control logic I've developed, and it runs through the models. And then at the end of the day, I'm looking at HVAC energy, PM 2.5 exposure indoors for the students, and then effective air changes per hour for respiratory aerosols. So here's the outputs from the model. So this first one here is HVAC energy. On the x-axis is the 14 cities I mentioned. So yeah, these are all, these are all pretty major cities. The difference being the variation in climate. The bar here this is cooling energy. The red is heating energy, and they're stacked. This is the average over 5 years, and the little error bars represent one standard deviation for how that energy would change over the 5 years. So it sort of shows you like how much energy varies over that 5-year period. So what we see here is that the controller is designed to basically have no impact on heating. We're trying to bring on excess air when it can benefit us for cooling. There's really nothing that can be done in that way for heating. All you can do is try and limit your outside air for heating when you're trying to heat. So you can see basically, there's no appreciable change for heating. And we do see some savings for cooling energy. So, and that's going to be greatest in the West where the climate is dry and we have the most economizing potential. So if we see here, like in Phoenix, if we run a state-of-the-art situation, we essentially do the best from energy. We're pulling in outside air for economizing. And the IAQ energy controller doesn't do quite as well. And that is because it is specifically limiting outside air when PM 2.5 is high. So we lose some of that free cooling potential in favor of protecting health, right? But we still do better than a fixed ventilation scenario. So you can see here the energy impacts are small, but there's a few hundred kilowatt hours to be had. And what's important to remember, I'm only proposing a control change, right? So there's not like you got to go put in a whole new HVAC system or something to get a couple hundred kilowatt hours of savings. Essentially, it's a back end programming change.
Theresa,
Yeah.
did you try changing the cooling set point for economizing to get the building colder anyway? I have been fussing with parameters But
to
this
see
does
like
not
if this can
reflect-
be, there might, I might be able to do a little bit better than this. And I don't want to get into all the details of simulation, but I don't think this is far off from the truth. Yeah.
And then, Theresa, where would the controller get the PM 2.5 data?
I'll show you, because this is a model, but I have a real world installation too. Okay, so PM 2.5 exposure, the gray bars are outdoor levels. Just for reference, the outdoor annual limit of exposure, according to the federal regulation, is 12. So you can see, like, for example, here in Stockton, there's non-compliance with the federal air quality regulations. That's probably no surprise. The fixed ventilation, you can see the fixed ventilation. If we use an economizer and demand control ventilation, we go up in PM 2.5 exposure, as you would expect. And if we apply the IAQ energy controller, we nudge that back down. Compared to the fixed ventilation rate, I currently have a PM increase of around 0.4. Oh, I forgot the units there. That's micrograms per meter cube. There's a lot of knobs I can turn in the model to fine tune whether we want to prioritize energy, PM 2.5 exposure. And so that's kind of in the process of what I'm working on. But what I've been doing here is setting up a framework to be able to analyze this. And lastly, one of the big targets here, I should mention this is funded by Flu Lab. Their goal is to reduce infectious disease transmission. Going from the fixed ventilation scenario to the IAQ controller, I'm able to get a mean increase of air changes per hour, essentially get a 1.1 increase in air changes per hour, while saving a little bit of energy and essentially being neutral on PM 2.5. So real world. So first, I laboratory tested this complete approach in a scaled building system we have in our lab. I'm not going to go through those details in the interest of time. But one of the things that became evident that was needed was a better control for this concept of doing demand control ventilation and maintaining carbon dioxide at a set point. Current controllers don't do that very well. And so I developed my own approach for just the simple need to just change a ventilation system rate to track a CO2 set point. And that's published. And so if you're interested, you can go read that. It's open access. Okay, so then I installed the complete system in 2 classrooms in California's Central Valley. These were packaged rooftop units. They already had modulating outside air dampers. They already had a trained building energy management system, managing their outdoor air controls. They were just at a fixed rate ventilation with an economizer. They were fixed rate ventilation with an economizer. We added communicating portable air cleaners from wind. And the experiment was designed that every week there's 2 classrooms. One operates at fixed ventilation, one operates the IAQ controller, and then every week they switch.
Theresa?
Yeah.
Can I ask you a question? So, in my experience in like real commercial buildings, there's 3 dampers that control that. Outdoor air, the exhaust damper, and the mixed air damper. And on a lot of HVAC rooftop units I've seen, there are not 3 dampers. There's only maybe 1 or 2 to try to vary the fraction of outdoor air.
Mm-hmm.
On those train, how many dampers were there?
I actually have a picture on the next slide,
Okay.
so I'll show you that. So this is what the installation looked like. So this is with the existing thermostat. We added a CO2 sensor, which we needed. Kelly, you asked earlier, we pulled data from the closest Air Now station, which was, I don't know, 2 miles away. You could also use a local sensor, but it's a trade-off between, do you want sensor accuracy or do you want location accuracy? And you essentially have to make that decision. So we're using the Air Now network, which has an API, an automated programming interface. You can essentially just pull it once an hour, it updates. The control algorithm that I wrote was programmed on Train's backend. What it does, what its outputs are it sets the outdoor air damper position. This is the voltage that goes to the outside air assembly, which there's a picture coming up here. And then it also sends a signal to this Wi-Fi connected wind air cleaner telling it what speed to run at and also like what color the light should be. Sends its little commands to it. This is a picture of the outside air damper. This is the outside air intake. There's also a return, and they're all on one gear system. So one actuator modulates and it balances the outside air like opens and the return air closes. And then there's just a pressure relief exhaust flap thing. So there's
two dampers.
2 dampers, yeah, they move together, 2 linked dampers.
Got it.
We had to do some maintenance. One unit was leaking refrigerant. We had to replace the filters. We found that one of the outdoor air assemblies was broken. The polarity of the outdoor air damper was flipped in the controller, so we thought open was closed and closed was open. Anyway, and then we had like an outside air relief stuck. So I just want to let you know that like the field's just kind of rough, and it's great to sit around and model like how controls should work, but like you really have to get a lot of things, just basic maintenance right before you can ever hope to achieve what you want to achieve. Yeah.
Sorry, I keep interrupting you.
That's okay.
Infinitely interested in, so, yes, that's my experience all the time.
Yes.
The economizer control rarely works.
So there's, you got to get all those, if the outdoor assembly doesn't do what it's supposed to do, then controlling it serves no purpose. It wasn't really that much work to fix these things, you know, it was, you know, like an hour, I mean, Tim was there.
Yeah, Hammer was involved.
Yeah, it wasn't a ton of work, but yes, Tim was, MacGyvered everything. We monitored, everything. Robbie was there for that. And Graham. And so basically we're just sensing everything we want to know about the HVAC system and the room and logging that once a minute to a data logging device. And then that goes up over cell network to a actually goes to a box folder every night. So we started data collection December 1st, and it's still ongoing. So I've got 15 weeks of data collected. So far, we've been essentially doing periodic review of the data. We've had just some very minor issues, like we've lost communication with the portable air cleaner twice, and Dave was there. He's fixed that one. So everybody's been to this school. And you know, like one time I just had to ask the teacher, like, hey, you shut off power of your portable air cleaner, can you turn it back on? And once the air now signal disappeared, but then it like came back all by itself. And so we have a lot of work to do to process the results, but I want to show you just 3 days of operation so you can see in general what's happening. So this is, everything I'm showing you is winter because we haven't really processed the spring data yet. So here on the left is the fixed rate ventilation. So you can see the green line is the position of the outdoor air damper. So in the morning, school opens, right? Or they turn it on at 7 a.m. You're supposed to turn your outside air before the students come because so you can remove contaminants from the room. So the outside air turns on. That's the green line. The red is calls for heat. The blue is calls for cool. So the outside air comes on to a minimum and it just stays there. The students come in and out of the room and CO2 gets as high as almost 1,600 parts per million. Ideally, you want to stay below like 1,100 if you're meeting building code. And because of the students being in the room here, you know, we had 3 calls for cool even in January. Over here, the UC Davis algorithm is what I'm calling it here. The students come in, it's modulating the outside air damper here as it needs to maintain CO2 about 1,000. And because it's using extra ventilation to maintain this CO2 set point, you can see here that we reduce the calls for cooling perception.
Yeah, why didn't they economize in that?
Yeah, they must have disabled the economizer on this.
And then the other question I had was,
Yeah.
did this school already run their fan all the time? Because that's an issue, right? Where
They were running their fans all the time. You have to run your fans in commercial buildings all the time to be providing ventilation all the time. Yeah, so this is just, this essentially is case A in my simulations. This is just fixed rate ventilation. We're not using the economizer in the field study. The PM 2.5 was high on this day. And so the algorithm is using enough ventilation to stay at 1,000, but it's not economizing because of the PM 2.5. So here's another day where PM 2.5 was high again. And this was another winter day. And again, you can see this is just showing you the variation in CO2 in the standard room, and then the UCD room on the right here, you can see the ventilation control is doing a nice job maintaining here at 1,000 parts per million. And I guess, you know, this is really exciting because although it seems trivial to run a DCV control to stay at 1,000 parts per million, I dare you to find a installation where that actually works very well. So I essentially am just proving we really can do DCV and do it well. And then here's another final winter day where the PM 2.5 was very low. And so now we have access to all the free cooling we want. And so the damper opens to 100% for large portions of the day, drives the CO2 down to like 400 to 600, right? And this is not just when a call for cooling is required, right? This is when, essentially anytime the outdoor air is within range. And the important thing we're looking for here is that we're not unintentionally triggering a call for heating by bringing in additional outside air. And that's it. Other questions? Yeah.
When PM 2.5 is high, I assume your 1,000 ppm CO2 set point could potentially go up.
Yeah, when it gets above, I currently have a program, I think when it gets above 35, it actually goes up to 1,700.
Oh,
Yeah.
and is that supported by ASHRAE or anyone else?
It's consistent with the new sort of like because then when that happens, then the air cleaner runs on high.
Got it.
So you're getting your respiratory aerosol removal. It's not technically allowed by like California building code, but it's consistent with the ASHRAE 241 approach, which, yeah. Okay, I don't know how I would see if there's anything happening online. Oh, or there's a chat. Okay. Oh, okay. I'll see what you shared. Okay, I'll turn it over to Aref. Oh, yeah.
One last question. I was wondering, is there anything that makes it very specific for commercial buildings, or can you apply the same methodology to residential buildings as well?
You'd want to do some, I have lots of thoughts about residential, but the approach is super different because it's not densely occupied, right? And you have all different things happening, right? Like you generally want to get rid of PM 2.5 from cooking, right? And you want to figure out how to cool down the whole thermal mass of your house at night in the summer. And there's all different. Same optimization is possible. You're just totally optimizing for slightly different parameters. You're less concerned about respiratory aerosols between you and like random people. You also generally don't have a ventilation system. Yeah.
So when you say you want to get rid of PM 2.5 from cooking, is that only if they have a gas stove?
No, cooking generates a lot of particulate matter.
That's what I'm asking. I didn't know that.
Oh, it's terrible.
When you burn things or
Like
just
oil
cooking in
frying.
general?
Oil frying and stuff.
Oil frying.
Put it out.
All of
the
that
time.
stuff.
All the time. It's worse if you burn something, but yeah, if you put a PM 2.5 sensor in your kitchen, you'll be.
I had the PM 2.5 in the house, our house over COVID, and anytime we cooked, we were like the worst PM 2.5 in Davis.
But that was with gas too, right? So
The gas.
Our stove is a.
Oh, really?
The particles generated from the gas combustion, you generate a lot of NOx, but the particle generation is.
And so it was probably like 15 feet away from the stove and just like the kitchen.
Did you email me your presentation?
Yeah, so is it advisable then, anytime you cook on your stove to run the fan?
Oh, yeah.
Yes,
100%.
yes.
Well, I didn't know that.
I mean, my
Well, we
fan
just
doesn't
saved
even
your life
run
today,
outside.
Kelly.
Yeah, it shoots right in your face, right?
I
Yeah.
know.
Oh, that's
It's a filter.
that's terrible.
And
The system
because I
don't
think
work.
for electric stove, they don't really mandate
Yeah.
throwing it outside, so it's
Oh,
just
really?
shooting me on the face, exactly.
Yeah.
Well, now, current code
You're
mandates
like me,
it has to
you
be
don't-
exhaust
Oh, is it?
system.
We didn't know this.
Not only that, but the fan doesn't really pull in the gases either. It just kind of bypasses it, it just kind of goes around it.
It
So
goes around
even
it.
with the fans on, yeah.
All right, you gonna come present?
Yeah.
How come no one's eating the food? People are allowed.
So we are so engrossed in your presentation.
You guys want to grab food before I start?
Yes.
Oh, look, individually wrapped pickles.
Oh, that's nice.
There's one here.
You're proposing variable speed fans for bars and stuff, right?
For comments.
Maybe if there's such a
Yeah. No, for what?
I would just wondering.
Could you do?
Just one person for bridging the gap there.
It's just the volume of air.
Help that stuff.
Oh, the recirculated filtering.
Oh, my part, well, that's
It's like
just.
a really big
Yeah.
Yeah, don't worry about that.
Yeah, no, I think
Are you sure it's like
without
really?
when we would have been.
Yeah, you can put that in though.
And
Oh,
do
you can
more.
plug this in, sorry.
Yeah, I found it after I started.
Theresa, what's the CO2 like health level that you're targeting? And removing it being, how
Um,
much of a health benefit is it?
The CO2
Probably.
The CO2 itself is a questionable risk. It's the fact that CO2 levels are correlated with respiratory aerosols. So as we start, if we put in more people and we talk more, our CO2 levels go up, but also our respiratory aerosol generation goes up, and that would spread infectious disease. So
Okay.
that's why I'm looking more at that equivalent air changes per hour, because when we filter, we remove those respiratory aerosols, but we don't remove CO2.
Okay.
More than 200 about that.
On the middle of it.
Oh, there you are, yeah.
Oh, yeah. There's gotta be an updated logo.
Huh?
There's gotta be an updated logo.
And that one.
Not sure what.
Logo, please. Logo.
I don't know, there's different ones with different people.
All right, hello, my name is Aboud, and today I'm presenting on the modeling and laboratory testing of PCM enhanced insulation. This one collaborates with Theresa and Dr. Marianne. I'd also like to thank our sponsor, the California Energy Commission, and acknowledge some assistance we had from engineers such as Austin Marshall, Derek Ross, and Siobhan Freeman. So you guys have probably heard this multiple times by now, but I'm going to start off by saying, what is PCM? So PCM is phase change material that is engineered to melt and freeze at temperatures advantageous to thermal energy storage. Now, when that's applied to the envelope applications, you can have advantages such as stabilizing wall temperature, as well as adding additional thermal mass to it. Going through a quick example, you can imagine a spring day or winter day where you have cold mornings and nights, but you have large solar incident radiation on the wall during the daytime. The PCM will start the day frozen. As the sun rises and as the wall warms up, heat will transfer through the wall into the PCM. That PCM will raise temperature into the melting point and it will start melting. As it melts, it'll absorb essentially all that heat flux up until the point where the sun goes down or temperature of the wall goes down far enough. By the time the sun goes down, it'll either be fully melted or partially melted. At that point, interior temperatures of the house may drop and the PCM could discharge into the home, one, stabilizing wall temperature, and two, possibly reducing the amount of energy you need for your gas furnace. So now for the overview of the project, what we're trying to do here. Essentially what we wanted to do was devise a retrofit solution, which took advantage of current retrofit applications. So we wanted to improve comfort and reduce energy use in existing California homes that were uninsulated. So this process involved drilling holes in the wall cavity, 3.8 centimeter holes, sealing leaks and cracks in the wall using aero barrier technology, reducing infiltration, apply blow-in insulation, specifically I think it was our R15 from model, or I think. Once that's done, we would have filled and sealed the holes, applied PCM to the exterior of the wall, and then put another sheet of gypsum on top of the PCM to return the home to the aesthetic state that it was in previously. This is kind of the layout of what it would be on a top-down view. So you have stucco, plywood, you have your wood frame insulation, gypsum, PCM, which is a thin layer, then another layer of gypsum.
Adam,
Yes.
do you know what year that Title 24 started requiring insulation in California homes?
1978,
1976.
78.
78?
Yeah.
So if your house was built before 78, you probably do not have.
Yeah, you probably don't have insulation unless you some homeowner before you put it.
Thank you.
So the research question and goals. So the question was, how does PCM perform as a wall for retrofit, and how can this performance be modeled essentially? And what are the energy impacts for California in general? So to address these questions, we had a few different steps. First, we wanted a simplified Energy Plus model that can just do whole year energy simulations. We wanted to validate that model using two things: one, 3D modeling, so Fluent, as well as laboratory testing to validate some of the assumptions for Energy Plus. Lastly, we wanted to do field tests in California homes, specifically be installed in Los Angeles, Sacramento, and Vallejo. Just as a note, I'm not going to be discussing the field tests in this presentation just for sake of time, but if you guys have any questions, feel free to contact me afterwards. So the general approach to modeling, we had wall geometry variations. We had a baseline wall, and we had a PCM wall. The baseline wall was just your standard gypsum to console layer to gypsum again. The PCM was that exact wall, but with PCM added. We modeled a building in Energy Plus and simulated an entire year. We then looked at the entire year and picked select days that we wanted to represent specifically in our laboratory testing and our Fluent testing. These were days with high temperature variation or days that we knew that the PCM was going through phase change. We chose those days, we went ahead and we inputted that data into our test grid or our laboratory apparatus. And we applied the temperature to the wall, and then we measured heat flux through it and compared that heat flux to what Energy Plus was essentially trying to say what the heat flux was. If that didn't work, we went back to our model and tweaked it. If it did work, we went on to the analysis performance of the entire year. So here's a construction of the baseline wall, both in our laboratory and our modeling. It's just your standard wall with studs 16 inches apart, about 20 millimeters of stucco, 12.7 millimeters of plywood, about 90 millimeters of wood, fiberglass insulation, and then like a gypsum. At Energy Plus, we had that exact same wall, obviously with the blended console layer. It had 3 thermal zones. It had an occupied space, an attic space, and a crawl space. It had 81 meters squared of conditioned space, with 20% of the exterior wall being covered by windows. That's the average for California. We had an attic installation of R38, insulated floor R19, a single speed split air conditioner of 3.4 CLP at 35C, 25.5 degrees Celsius cooling set point, and natural gas burns 0.78, and fuel utilization efficiency was 19.5 degree heating set point. And this is the mock-up that we have for the house. This is the exact way we modeled Energy Plus. That's what it looked like. Now going to the actual construction for the laboratory test, this was our sample. It was essentially identical to what I've shown you before. The main difference is we had 4x4s instead of 2x4s. That's because if you can imagine on your wall, you don't just have studded cavities, right? You have window framing, you have top framing, bottom framing. So we wanted to essentially accommodate for that. So we took a general, typical wall compensation. We found out the percent wood that would be in that wall, and we tried to match that. With our laboratory sample, we got about 22%. Now going on to the dynamic heat flux measurement apparatus. So as I said before, the idea was we wanted to apply a temperature to the indoor side and outdoor side of that wall temperature or that wall sample and measure the flux going through. So the way we did this is we had 2 big heat spreaders controlled with TECs, which if you didn't know, they're just, they're called thermoelectric coolers. You're able to essentially have a hot side and a cool side, you're able to control that temperature of the TPC using voltage and voltage polarity. So we control those heat spreaders to the temperature profile as directed by Energy Plus, and we used heat flux sensors on the outside to measure that flux going through it. We measured that flux over the average of the, we measured that flux over the wall. We weighted it based off composition. And then we compared it to Energy Plus. This is a quick mock-up. This is the 3D model, and this is the real-life sample. Going into actual control, starting off at the left, you can see the solid lines are what we actually measured the squares of what Energy Plus. There, you can see we're able to match the temperature profiles very closely. For the case of the baseline, we had an indoor air about 0.12%, and then a little over 1% from the outdoor. Outdoor just has higher temperature fluctuations, so hard to match. So with that, we knew that we were imposing temperature properties. So we were like, okay, we can look at the flux now. Looking at the flux of the outdoor, we saw that once again, we're matching the desired results from Energy Plus. So this is essentially validating what Energy Plus is telling us for the outdoor, same for the indoor. I want to mention, we also did a fluent analysis here for 3D fluent studs and 3D blended studs. We wanted to make sure that the 1D assumption of Energy Plus was correct. So we had that 3D modeling and compared it to these results as well. Once again, they match. So we were confident that the conduction analysis from Energy Plus is accurate and that the 1D assumption is accurate. So we were saying, okay, now that we know this, we can move on to PCM. So going into PCM, we had a few different options that we could have chosen at the start of the project. We had Saint-Gobain, which is a plaster embedded encapsulated wax-based phase change material. Unfortunately, I think it was emitting formaldehyde. Is that what it was?
The plaster specifically was.
So what ended up happening was this was discontinued, and there was no replacement project or no replacement product. Enco was another option. They're a salt-based, non-flammable phase change material. But they were a startup company. This product was being tested. It wasn't mass scale, so they weren't able to give us the amount of material we needed. So we weren't able to go with them. That led us with Insul Corp, which was already being mass manufactured, at least for industrial use, I think in roofs. It's a salt-based, non-flammable phase change material containing a plastic housing, given multiple form factors, 24 by 4 and 16 by 24. And this was readily accessible. We were just able to buy it off the shelf. In addition to these, we're constantly looking for different technologies that came out during the course of the study. But as we progressed, Insul Corp remained the most applicable to what we're trying to figure out. So going with Insul Corp, this is the properties of Insul Corp. As you can see, we had a solid conductivity 1.5, liquid 0.5, 3.5 specific heat, 4.5 liquid. You have different properties for the different states. Density 1.5, like 175. So essentially, PCMs are oftentimes designed with these hysteresis in mind because you're essentially maximizing that phase change area. And when you're doing that, you're blocking the maximum amount of heat. So if you look over here, you can see that the temperature as it melts up, it melts at actually a higher temperature and then it freezes at a cooler temperature. So this essentially tries to maximize the amount of time that you're within that melting range when it's installed in a house, and maximizing the thermal storage. This was a discovery made about halfway through the project, and it was the source of a lot of trials and tribulations, especially with the base Energy Plus model, which I'll discuss later. As for the actual wall construction, as I mentioned, it's the exact same wall as the baseline. We just added Insul Corp PCM panel to the outside and then another layer of chips. So if you look over here, it's just PCM and then chips. So this is what the actual panel looked like. These squares are the actual encapsulated PCM, but what is a little hard to model is these channels. These channels are used for mounting specifically on walls. So what we did is we did a surface calculation for our modeling results, and we only used about 56% of the full thickness of the PCM for the model. So I think we used about 3.2 millimeters of PCM rather than the full thickness, just because we wanted to accurately represent how much thermal mass was in the This is just discussing the main model or the main model Energy Plus. So the model that comes based with Energy Plus, we used I think Energy Plus 9.5 or something like that. The main model that came with Energy Plus, it doesn't work fundamentally. It doesn't conserve energy. It generates and destroys energy consistently. And this was it just did not match lab results. We just kept hammering away until we figured out that the model itself was wrong. But during our search, we actually found an alternative model that was not published, or that was published, but it's not an official release, by Feng et al. And this was able to accurately model the hysteresis, and it also implemented subcooling, which I can describe later if anybody's interested. Going on to the laboratory results, once again, very good temperature match. Moving over to the outdoor wall, we had great flux measurements to actual measurements. These peaks are kind of hard to hit just because there's rapid temperature variation. The outdoor wall is a little bit better just because of the distance from the PCM. But moving to the indoor wall, which is close to the PCM, we did have some variation away from the curve. But overall, we were able to match with consistency that we were happy with, and we were able to essentially call the model valid. Yeah.
Could you slow down and just describe what's happening with those peaks and
Yeah, of
stuff?
course.
Why they go up and down? What's happening?
So this is a 5-day, temperature profile.
Okay.
So you have the start of the day, which is at 0, and then you have the sun hitting the wall, hitting up the wall. This is moving at outdoors, and then it's just cycling over the course of the 5 days.
Is that outdoor air temperature or
This is outdoor wall temperature.
outdoor wall temperature?
Yeah, this is what was directly imposed on our wall sample.
Okay.
This was the south facing wall.
Correct,
in
this is the
Energy
south.
Plus.
Yeah. And then you can see there's a bit of a temperature lag as we use this bit of hot peaking just for the heat to transfer. While looking at the flux, any negative flux is heat leaving from the wall, so going from the inside out. Positive fluxes are going from the outside in. Once we were confident with that, we wanted to move on to the full year energy analysis. And we wanted to test a few different measurements and their effects on PCM. So we wanted to vary things such as, in this case, it was wall insulation. So we measured wall insulation and how essentially it affected HVAC energy. We have heating on the bottom, cooling on the top. We converted heating to kilowatt hours just for consistent plots. As you can see, adding insulation from R0 to R7 to R15, you have diminishing returns, both heating and cooling. But what's interesting to point out is that PCM has a much greater impact, despite it being somewhat small, when wall insulation is lower. So as insulation increases, the effect of PCM increases across thicknesses. So if you go from top to bottom, you have you have no PCM all the way up to max thickness PCM, which I think was what we modeled, just 3.2. The green line is what we ended up actually including in our annual energy model. So we did the same analysis for a few different parameters. I'm going to start with the right over here. We had a leakage area. So this is an unsealed home. This is a sealed home. The effects of PCM doesn't really change as you go with sealing, but you can see that the standard cooling cost increases, heating cost decreases because you're losing on that free cooling. Going down to internal mass. This theoretically should be increasing the internal mass of the home, which should decrease HVAC energy. So we wanted to measure how the effects of PCM changed with increasing thermal mass. You see at the lowest amount of thermal mass, PCM is as most effective. Again, going from least PCM up here, most PCM down here. And as you increase thermal mass to, this is square feet of plywood. This is how Energy Plus measures it. Going to maximum thermal mass, you have essentially negligible differences with the addition of PCM. This is what we modeled. This is what the DOE recommends. Going on to ventilation, this is a bit hard to explain, but ventilation is measured and varied by total window open area for this specific case. As you can see, adding ventilation drastically increases, drastically decreases the amount of cooling energy needed. As you increase, increasing ventilation drastically decreases cooling energy needed. But we're able to keep the amount of heat needed constant just because we had essentially a mock controller that only opened the window when it was advantageous. In addition, as ventilation increased, it also increased the effectiveness of the PCM, as you see here. So it's only slight, but it does allow you to essentially charge the PCM or freeze the PCM at will during times that are advantageous. And this was needed just to ensure we had free cooling movement. Going on to the full year energy analysis. Just to note, this is additive. So the orange bar is uninsulated. Then we go to adding insulation, to adding ventilation, to adding sealing, and PCM. So each of these steps build on the previous. Obviously, the biggest step is just insulating the home. You see your massive peaks here drop substantially. After that, the next step is ventilation and sealing. Both decrease energy use, and then PCM marginally decreasing energy use for both heating and cooling cases. And this is across all CZs. It varies depending on cooling and heating dominant climates, but overall PCM does enhance the retrofit, but fairly marginal, especially compared to the other retrofit steps. Going into monetary savings and payback period, just to note that this is based on a field installation, so this is based off quotes from the LA home, as well as just different standards of costs. We modeled costs based off of square footage of the home as well, so square footage of wall area. So we were able to essentially say that, you know, the cost per square foot would be 2.25, 0.99, 2.8 for the different steps of the retrofit process, which is blood insulation, ceiling, PCM, and drywall, and wall finishing. So yearly monetary savings with each step, obviously, yearly monetary savings increases with each step here. So adding blood insulation, ceiling, PCM, drywall, wall finishing and painting, or not wall finishing and painting, but PCM and drywall, increases your HVAC energy, increasing your HVAC energy savings with each step. But I think a better qualitative, or a better quantitative measurement to look at would be the break-even time. So obviously adding insulation is good, but when you add ventilation and ceiling, your break-even time actually decreases for a retrofit. But adding PCM, it increases your break-even time. So it's not as worth it, but oftentimes the payback period for everything is below 10 years. But I guess the question is, how much efficiency do you really want to squeeze out of your envelope, and what's really worth it at a certain point? But overall, you can still see that you get paybacks eventually. For places like CC1, maybe it's not worth it. You got the 40+ year break-even time, but going down to like CC15, your break-even time is less than 5.
Where are we? Where's Davis?
12.
12.
Right
Right
here. So what's the payback of insulating an uninsulated wall?
The payback period on an insulated wall is roughly 8 years. I don't have the number right off the top of my head, so.
Yeah, I mean, just approximately 8
Yeah,
years.
yeah.
That's drilling the holes and blowing the
Yeah.
insulation.
Yeah, and
What's
this,
happening in the attic? In this model? Is there insulation in the attic?
this is just adding wall insulation. This is with assumed attic insulation. Yeah.
Okay.
With attic's already insulated. I do want to note that what makes PCM advantageous here is assuming that wall finishing and painting would happen regardless of whether PCM's added. Because obviously you're gonna have to patch those walls and paint. So it's kind of leveraging that additional cost to make the payback period more worth it for PCM, because obviously the cost is fairly high comparatively, just for materials mainly.
Oh, wait, this is stucco, so the holes are coming from on the inside.
Yeah, the holes are coming from the inside. Yes. Going on to the impact of PCM on wall temperature stability. So wall temperature stability greatly relates to thermal comfort of the home. As you can see, adding insulation plus ventilation and ceiling narrows that temperature spread on the wall quite drastically, but adding PCM narrows it even further. So there is evidence that we would see expected thermal comfort, and I think that was reflected by our surveys for the residents for the field installation. Now, one major talking point that we heard from manufacturers was that there's not really a good number to advertise to residents to say, oh, if you add PCM, you're getting this increases in insulation. It's kind of hard to describe. So what we aim to do was essentially create an equivalent resistance value that can be advertised to customers. The way we did this is we had that R15 insulation, and then we added the PCM. We measured that HVAC energy saving. And then what we did is we took the PCM off and then gradually increased the base R15 all the way up to see where that energy savings match. And we found that curve intersection, and we were able to determine that, okay, adding PCM with R15 had an equivalent R value of X for the different seasons. As you can see, it varied greatly. We had anywhere from R18 to R60. And there's some cases we couldn't really measure it just because the addition of insulation just didn't really have a stable curve to be able to match it to. And we point this out because new constructions are required to have 6-inch studs. to have an equivalent R21. And that greatly increased construction costs. So we're proposing that there could be an alternative here of having the traditional 4-inch studs with PCM to achieve that R21 value in certain climate zones, while still maintaining that 4-inch stud and reducing construction costs.
What thickness PCM, sorry,
Pardon me?
what thickness PCM did you?
About
The big-
half,
yeah.
roughly half an inch, about like 0.62.
I'm sorry, I don't understand those numbers. What does the 18 mean in that first box? Yeah,
Right here?
yeah, what does that mean?
So if you could imagine, you have a wall with increasing insulation. You're increasing your R value over time. So what we essentially had is we had that base R15 with the 4-inch stud and applied PCM. We measured HVAC savings from the PCM and the R15. And then we found an intersection point with just adding insulation
So
to find an equivalent.
so that 18 means that it was the same as an additional R3.
Correct, correct.
And that 60 in there is an additional R45.
Yeah,
The thing is, it's really diminishing returns. The energy consumption of R60 versus R18 is very, very small. But essentially, it is the equivalent of R60.
yeah. So going back to this curve, we had first, probably for that CZ, you had a massive flattening for additional resistance values. So, I mean, you only really have to cross just a
And I want to
percentage to.
add on the manufacturer desire for an equivalent R value is really about, is I think more about code compliance,
Exactly, yeah.
right? If you put PCM in, like they keep tightening the code to try and get a specific R value, but the PCM does not have insulating properties, it's just storage. And so we basically ran the numbers to say it's the equivalent of this amount of
In
insulation.
terms of HVAC savings.
So what do you attribute that number to? Is it because the climate has a very comfortable, like a diurnal swing that lends itself to PCM better?
Yeah, it just had more hours of temperature range that was within that hysteresis, right? So you have more savings. And it's also
The
dependent,
freeze thaw was happening more.
what's happening more often, exactly.
And what was the nominal melt temperature of PCM?
For our case, it was 71, around 71.
71 after.
On average, yeah. Just to go back a couple slides, we did ensure to account for that. So looking specifically at these temperatures, around 20 C is what we were specifically concerned with in terms of validating energy plus. References that before any questions?
Yeah, so is there interest from McAllister and the Title 24 people, especially for those climate zones where it's equivalent to R60?
Yeah, there is. We had a meeting with the CEC and I forget what program that they use. Theresa, do you remember?
CBAG.
Well, there's interest for new construction. I think as a retrofit, it's just very cumbersome,
It's super
but
costly.
yeah. The other issue is the current form factor needing to go into the retrofits, but it's not. The manufacturer needs to do a little bit of work to make it look like drywall. And right now, it doesn't look like drywall, it looks like plastic panels. But
What if you put it in the wall cavity in new construction? Like fit it nicely between the studs? Hide it? I mean, you're losing some insulation.
Yeah.
no, the whole project was retrofit driven, so we didn't model I mean, it's conductive.
I mean, as far as the arguments to
So-
the Energy Commission about and to the construction,
You just have to be
Disagree.
careful with you'd have to do the modeling because, we were trying to store the energy
right?
And then you also,
in the home.
I know, so you'd have to put it on the back of the drum.
yeah, then you also lose the thermal comfort factor. It's not gonna stabilize wall temperature as much. It's gonna be a lag.
You got a question there? Well, thank you.
Dr. Narayanan asks if the homeowners just retain the PCM as of now, yes. Most of them are incredibly happy. They report better thermal comfort, HVAC energy on average decreases, but you also have to understand that this was an addition with, they were most of them were completely uninsulated. So this is with the addition of insulation. So of course, they're gonna feel better regardless, but, none of them have complained about the addition of PCM.
Okay.
Great work, thank you folks.
Costs for electric, you know.
Just PG&E, they had some kind of. Yeah, that was projected, those projected. Or not projected pieces, projected. The average peak and then
Oh, like time of use.
yeah,
and then-
for 2024.
It's always hard to choose the number
Yeah.
for that, and I'd rather choose one number than try to deal with.
The range, exactly, yeah.
Aref, let's,
Bills and total.
one,
So if your recommendation is to go from 6-inch studs to 4-inch studs with addition of PCM. There's one manufacturer of PCM that
Yeah.
sells in the state.
Yeah.
Yeah,
And that's for only new builds, right?
correct, yeah.
Is there any kind of like estimated cost savings to it? Like, is that a significant cost savings?
I don't.
Yeah.
I don't
we
think
did it for the
6-inch studs should cost more to the builder. I think the argument is that there's the same amount of lumber. It's just because you space your studs 24 inches apart.
Mm-hmm.
So I think the argument is that it should be the same cost as 4-inch studs, but builders are, adverse to change, right?
We were saying with 6-inch studs, they put them 24 inches outside.
Yeah.
Yeah, they do.
Cause they,
I don't think it's material costs as much as like general like labor.
That gives you
costs,
better
right?
insulations, like the wood, that
Yeah.
wood surface area,
Increases.
well, I mean, the
Well,
amount of bridging that occurs in that is lower.
And you also have the increased thickness, right? So the conduction.
And
part,
the
yeah.
thickness.